Everything around you, including yourself, is made up of atoms. Atoms are the tiny building blocks that make up all matter in the universe. They're so small that millions of them could fit on the head of a pin. Atoms themselves are made up of even smaller parts, a central core called the nucleus, which contains protons and neutrons, and a cloud of electrons that whiz around the nucleus. The number of protons in the nucleus determines which element the atom is. For example, hydrogen has 1 proton while oxygen has 8. This simple difference leads to the incredible variety of substances we see in the world. Let's take a closer look inside the atom. The nucleus at the center is made up of protons and neutrons. Protons carry a positive charge while neutrons are neutral. Surrounding the nucleus are electrons, which have a negative charge. These electrons don't just float randomly, they move in regions called shells or energy levels. The arrangement of these electrons, especially those in the outermost shell, plays a huge role in how atoms interact with each other. The outermost electrons are called valence electrons, and they're the stars of most chemical reactions. Every known element is organized in the periodic table. This table isn't just a list, it's a powerful tool that tells us about the properties of each element. Elements in the same column or group have the same number of valence electrons, which means they often behave similarly in chemical reactions. For the main groups, the group number tells you how many valence electrons there are, except for helium, which only has 2. The periodic table is like a map for chemists, helping them predict how elements will interact. Periodic table is arranged in rows called periods and columns called groups. Elements in the same group share similar chemical properties because they have the same number of valence electrons. As you move from left to right across a period, each element gains a proton, an electron, and usually some neutrons, making the atoms heavier. As you move down a group, the number of electron shells increases, which affects the size and reactivity of the atom. This organization helps us understand trends in element behavior. Atoms of the same element can have different numbers of neutrons. These variations are called isotopes. Some isotopes are stable while others are unstable and break apart, releasing energy as radiation. This process is called radioactive decay. The number of protons always stays the same for a given element, but the number of neutrons can vary, leading to different isotopes with unique properties. Some isotopes are useful in medicine and science, while others can be dangerous due to their radioactivity. Atoms are usually neutral with equal numbers of protons and electrons, but if an atom gains or loses electrons, it becomes charged and is called an ion. If it gains electrons, it becomes a negatively charged anion. If it loses electrons, it becomes a positively charged cation. Ions are crucial in chemistry because they're involved in many reactions, especially those that happen in solutions. The periodic table helps us predict which elements are likely to form ions and what charges they'll have. Periodic table is divided into 3 broad categories: metals, nonmetals, and semimetals. Metals are found on the left side and are usually shiny, good conductors of electricity and malleable. Nonmetals are on the right and are often gases or brittle solids. Semimetals or metalloids fall along a zigzag line between metals and nonmetals and have properties of both. This division helps us understand why different elements behave the way they do in reactions and in everyday life. 2 or more atoms bond together, they form a molecule. If the atoms are from different elements, the molecule is called a compound. Compounds often have properties that are completely different from the elements they're made of. For example, sodium is a reactive metal and chlorine is a toxic gas, but together they form table salt, which is safe to eat. The way atoms bond and arrange themselves in molecules determines the properties of the substance. Chemists use molecular formulas to show how many of each type of atom are in a molecule. But sometimes, different molecules can have the same formula but different structures. These are called isomers. Isomers can have very different properties even though they're made of the same atoms. For example, graphite and diamond are both made of carbon, but their structures make one soft and the other extremely hard. Understanding isomers is key to understanding why substances can behave so differently. Show how atoms bond. Chemists use Lewis dot structures. These diagrams represent valence electrons as dots around the element symbol. Lines between symbols show bonds where electrons are shared. Lewis structures help us visualize why atoms bond and how they achieve stable arrangements. Atoms tend to bond in ways that fill their outermost electron shell, reaching a state of lower energy and greater stability. This is often called the octet rule, where atoms aim for 8 electrons in their outer shell. Atoms bond to reach a state of lower energy, just like a ball rolls downhill to lower its potential energy. The most stable state for most atoms is having a full outer shell of electrons. Noble gases found in the last column of the periodic table already have full outer shells, which is why they rarely react. Other atoms bond with each other to fill their shells, either by sharing or transferring electrons. This drive for stability is at the heart of all chemical reaction. When 2 atoms share electrons to fill their outer shells, they form a covalent bond. This type of bond is common in molecules like water and carbon dioxide. The shared electrons are attracted to both nuclei, holding the atoms together. Covalent bonds can be single, double, or triple depending on how many pairs of electrons are shared. These bonds are strong and give molecules their shape and stability. Not all atoms share electrons equally. Electronegativity is a measure of how strongly an atom attracts electrons in a bond. In the periodic table, electronegativity increases from the bottom left to the top right, with fluorine being the most electronegative element. When 2 atoms have a big difference in electronegativity, one can pull electrons away from the other, leading to different types of bonds. Understanding electronegativity helps explain why some molecules are polar and others are not. The difference in electronegativity between 2 atoms is large. One atom can completely transfer an electron to the other. This creates ions, one positive cation and one negative anion. The attraction between these oppositely charged ions forms an ionic bond. Table salt or sodium chloride is a classic example. Sodium gives up an electron to chlorine, resulting in a strong bond that forms a crystal lattice. Ionic bonds are among the strongest chemical bonds. Metals, atoms bond in a unique way called metallic bonding. Here, the valence electrons are not tied to any one atom but move freely throughout the metal. This sea of electrons allows metals to conduct electricity and heat and makes them malleable and ductile. The positive metal ions are held together by the attraction to these delocalized electrons, giving metals their characteristic properties. Atoms share electrons equally. The bond is called nonpolar covalent. If one atom pulls harder on the electrons, the bond becomes polar covalent. In polar bonds, one end of the molecule is slightly negative and the other is slightly positive. Water is a great example. Oxygen pulls electrons more strongly than hydrogen, creating a molecule with a positive and a negative end. This polarity leads to many of water's unique properties. Molecule with a positive end and a negative end is called a dipole. These electric dipoles can interact with each other and with ions, leading to interesting behaviors. For example, water molecules arrange themselves so that the positive end of one is near the negative end of another. This creates strong attractions between molecules, called intermolecular forces, which affect boiling points, solubility, and more. Hydrogen bonds are a special type of intermolecular force that occurs when hydrogen is bonded to a highly electronegative atom like fluorine, oxygen, or nitrogen. These bonds are much stronger than typical dipole interactions and are responsible for many of water's unique properties, like its high boiling point and its ability to dissolve many substances. Hydrogen bonds also play a crucial role in the structure of DNA and protein. Even molecules that aren't polar can attract each other through van der Waals forces. These are weak, temporary attractions that occur when electrons happen to be more on one side of a molecule than the other, creating a momentary dipole. These forces are much weaker than hydrogen bonds or ionic bonds, but they're important in many biological and physical processes, especially in large molecules. Water's polarity makes it an excellent solvent. It can surround and separate charged particles, allowing many substances to dissolve. However, water can't dissolve nonpolar molecules like oils and fats. This is why oil and water don't mix. The rule of thumb is like dissolves like. Polar solvents dissolve polar substances and nonpolar solvents dissolve nonpolar substances. This principle is key in chemistry and biology. Soap molecules have a polar head and a nonpolar tail. In water, the polar heads interact with water while the nonpolar tails surround grease and oil. This forms structures called micelles which trap dirt and oil, allowing them to be washed away. Soap's unique structure lets it bridge the gap between polar and nonpolar substances, making it essential for cleaning. Not all bonds are created equal. In order of strength, the main types are ionic bonds, covalent bonds, metallic bonds, hydrogen bonds, and van der Waals forces. Ionic and covalent bonds are the strongest, holding atoms together in molecules and crystals. Metallic bonds give metals their unique properties. Hydrogen bonds and van der Waals forces are weaker, but they play important roles in the behavior of liquids and biological molecules. Matter exists in three main states: solid, liquid, and gas. In solids, particles are tightly packed and only vibrate in place. In liquids, particles can move around each other but stay close together. In gases, particles move freely and fill any container. The state of a substance depends on temperature and pressure, as well as the strength of the forces holding its particles together. Temperature measures the average kinetic energy of particles, how fast they're moving. Entropy is a measure of disorder or randomness. Solids have low entropy because their particles are organized, while gases have high entropy because their particles move freely. Substances tend to be solid at low temperatures and high pressure, and gaseous at high temperatures and low pressure. These concepts help explain why matter changes state. Strength of the bonds holding particles together affects melting and boiling points. Strong bonds like ionic bonds require a lot of energy to break, so substances with these bonds have high melting points and are often solid at room temperature. Weaker bonds like hydrogen bonds result in lower melting points, so substances like water are liquid at room temperature. This explains why salt is solid and water is liquid under normal conditions. Beyond solid, liquid, and gas, there's plasma, a state where gas is ionized and electrons are free from atoms. Plasma exists at very high temperatures like in stars or under high electric potential like in neon lights. When ions and plasma collide, they emit light. The color of this light depends on the element because each element has unique energy levels. The range of possible light frequencies is called the emission spectrum. All matter can be classified as either pure substances or mixtures. Pure substances contain only one type of element or compound. Mixtures contain two or more pure substances and can be homogeneous or heterogeneous. Homogeneous mixtures look the same throughout, like salt dissolved in water. Heterogeneous mixtures have distinct regions, like sand and water. This classification helps us understand and separate materials in chemistry. Homogeneous mixtures are called solutions, where substances mix evenly like salt and water. Heterogeneous mixtures like sand and water are called suspensions, where particles are large enough to settle out. Colloids like milk are in between. The particles are bigger than in a solution but smaller than in a suspension, so they stay evenly distributed without settling. Understanding these types helps us identify and work with different mixtures. Chemical reactions are processes where substances change into new substances. They often release or absorb energy and can happen quickly like explosions or slowly like rusting. There are several types of reactions: synthesis combining substances, decomposition breaking apart, single replacement, and double replacement. All reactions happen to reach a more stable, lower energy state. Chemical reactions, the amounts of reactants and products are related by stoichiometry. This means reactions happen in specific ratios based on the conservation of mass. Matter can't be created or destroyed, only rearranged. To balance a chemical equation, make sure the number of each type of atom is the same on both sides. This ensures the reaction follows the law of conservation of mass. Atoms and molecules are so tiny that chemists use a special unit called the mole to count them. 1 mole is a specific number of particles, about 6.02 x 1023. This makes it easier to measure and mix chemicals in the right proportions. For example, to react hydrogen and oxygen to make water, you need 2 moles of hydrogen for every 1 mole of oxygen. The mole concept connects the microscopic world of atoms to the amounts we use in the lab. It's important to distinguish between physical and chemical changes. Physical changes alter the appearance of a substance but not its identity, like melting ice or hammering metal. Chemical changes create new substances, often with signs like bubbles, color changes, or explosions. Only chemical changes involve the making or breaking of chemical bonds. Every chemical reaction needs a certain amount of energy to get started. This is called activation energy. Some reactions need a lot while others need very little. Catalysts are substances that lower the activation energy, making reactions happen faster and more easily. Importantly, catalysts aren't used up in the reaction, so they can be reused over and over. Enthalpy is a measure of the total energy or heat content of a system. In chemical reactions, if the products have lower enthalpy than the reactants, heat is released. This is an exothermic reaction. If the products have higher enthalpy, heat is absorbed. This is endothermic. Exothermic reactions often happen spontaneously, while endothermic ones usually need a continuous input of energy. Predict if a reaction will happen on its own. Chemists use Gibbs free energy. This value combines enthalpy and entropy and depends on temperature. If the change in Gibbs free energy is negative, the reaction is spontaneous and releases free energy. If it's positive, the reaction is not spontaneous and needs energy input. This explains why some reactions only happen at certain temperatures. Some reactions can go both forward and backward. When the rate of the forward reaction equals the rate of the reverse reaction, the system is at equilibrium. At equilibrium, the concentrations of reactants and products stay constant, even though reactions are still happening. Equilibrium is common in phase changes and in acid-base chemistry. Acids and bases are important classes of chemicals. According to the Bronsted-Lowry definition, acids donate protons, hydrogen ions, while bases accept them. A molecule with at least one hydrogen it can give away can be an acid, and anything that can pick up a hydrogen can be a base. Some molecules can act as both. These are called amphoteric. Strong acids dissociate almost completely in water, releasing lots of protons and forming many hydronium ions. Weak acids only partially dissociate, resulting in fewer hydronium ions. The strength of an acid is measured by the concentration of hydronium ions it produces. This is where the pH scale comes in. A lower pH means a higher concentration of hydronium ions. pH scale measures how acidic or basic a solution is. It's based on the negative logarithm of the hydronium ion concentration. Pure water has a pH of 7, which is neutral. Values below 7 are acidic and values above 7 are basic. Each step on the scale represents a tenfold change in acidity. The pOH scale measures basicity, and together, pH and pOH always add up to 14. When a strong acid and a strong base are mixed, they neutralize each other, forming water and a salt. This reaction doesn't cause an explosion, but it does release energy. For example, mixing hydrochloric acid and sodium hydroxide produces water and table salt. Neutralization reactions are important in many biological and industrial processes. Redox or reduction oxidation reactions involve the transfer of electrons between substances. When sodium reacts with chlorine to form sodium chloride, sodium loses an electron, is oxidized, and chlorine gains one, is reduced. Redox reactions are everywhere from batteries to metabolism. The oxidation number helps track how electrons move in these reactions. Oxidation numbers are like imaginary charges assigned to atoms and molecules. They help us keep track of electron flow in redox reactions. There are some basic rules. Hydrogen is usually +1, oxygen is usually -2, halogens are usually -1, and single elements are always 0. The sum of oxidation numbers in a molecule equals its overall charge. By comparing oxidation numbers before and after a reaction, we can see which atoms gained or lost electrons. Electrons in atoms don't orbit in neat circles. Instead, their positions are described by 4 quantum numbers: n shell, l subshell, ml orbital orientation, and ms spin. These numbers define regions in space called orbitals where electrons are likely to be found. The Pauli exclusion principle says no two electrons in an atom can have the same set of quantum numbers, which limits how many electrons can fit in each orbital. The arrangement of electrons in an atom is called its electron configuration. Electrons fill orbitals in a specific order, starting with the lowest energy levels. The s subshell holds 2 electrons, p holds 6, d holds 10, and f holds 14. The order in which these are filled is called the Aufbau principle. Electron configurations explain why elements behave the way they do and help us predict chemical properties. Electrons in the outermost shell, called valence electrons, determine how an element reacts. By looking at the electron configuration, we can find the number of valence electrons and predict reactivity. For transition metals, ignore the full shells of the nearest noble gas and count the remaining electrons. This knowledge helps chemists understand and predict chemical reactions.